Hello everyone. Today we are going to be talking about logarithms, what they are, why they are important, and how to use them. At their core, logarithms are a different way to describe exponents. With exponentiation, we say that, for example, 2 to the third power equals 8. This is an equation written in exponential form. With logarithms, instead of thinking 2 to the third power equals what, we think 2 to the what power makes 8. This form is called logarithmic form, where the result isn't the total, but rather the exponent. Let's look a bit closer at the way we write logarithms. The expression begins with the word log, then has two values next to it. The subscript is called the base, and it's the same number as the base in exponential form. The number in the parentheses is called an argument, which is just a word to describe an input number, like a function. This is the total value we got from the exponential form. The number after the equals sign is the exponent, the number that is on top of the base in exponential form. It can be pretty overwhelming trying to take all of it in at once, so don't be afraid to pause and let it sit. Writing exponents a different way is odd, isn't it? Why do it another way when one way already conveys the same information? Simply put, logarithms allow us to describe information that grows exponentially in a more concise and human-friendly manner. By human-friendly, I mean to say that we as humans don't really grasp large numbers that well, and logarithms help describe that gap. If I asked you, how long is a million seconds versus a billion seconds? We know that a billion is bigger than a million, but they seem like similarly large values until I say that a million seconds equates to around 12 days, where a billion seconds is around 32 years. If we use logarithms to describe these values, then instead we have log base 10 of a million and log base 10 of a billion, which equals 6 and 9 respectively. 6 and 9 are the powers of 10 that make up a million and a billion. These numbers are a lot easier to grasp as a person, so when working with large numbers, logarithms make it possible to be understandable. Logarithms continue to be useful and show up in many applications, like the pH scale in chemistry, as well as a description of how long it takes to search and sort data in computer applications. There are many other reasons why logarithms are helpful, including the unique properties they have in algebra. We will look at just one of them, called the change of base formula. Something neat about logarithms is that we can manipulate the base of the expression much easier than if it was written as an exponent. For example, the logarithm on screen, read as log base 4 of 26, can be rewritten as log of 26 divided by log of 4. Notice the base in both of the expressions is x, meaning we can put any base in and the value is still the same as the original logarithm that we started with. The change of base formula is useful because often logarithms don't have a nice integer solution. In these cases, we use a calculator, but some calculators aren't advanced enough to have the ability to plug in any base that we want. Often, they only have two buttons, the common log and the natural log. These are equivalent to log base 10 and log base e, Euler's number. They have their own buttons because they appear so often in math. Let's go back to that previous example. If we wanted to find the value of log base 4 of 26, we would use the change of base formula to change the base to one that our calculator knows. So log base 4 of 26 is equal to log base 10 of 26 divided by log base 10 of 4. Now we can use our calculator on this problem, giving us a result of about 2.35. Let's do a few more. This is a more in-depth example. One bacterium sits in a petri dish. This strain of bacteria replicates every 30 minutes. Later, the petri dish contains about 130,000 bacteria. How many hours does this take? Well, after 30 minutes, the one bacterium doubles to 2. After another 30 minutes, it doubles to 4. It looks like we have an exponential growth with a base of 2, being multiplied by 2 each replication. The exponent, is the number of 30-minute intervals that have passed. Let's use logarithms to find the exponent. We have log base 2 of 130,000 bacteria. We can rewrite this expression using the change of base formula. Thus we have log base 10 of 130,000 divided by log base 10 of 2. Putting this into our calculator, we get around 16.988, or 17 replications. Each replication takes about 30 minutes to undergo, so we can use unit conversions to go from replications to hours. We have 17 replications times 1 replication every 30 minutes, and there are 60 minutes in 1 hour. So we can cancel our units. These cancel to 1/2. So our total is going to be 17 over 2, or 8.5 hours. Thank you for watching this video on logarithms. I hope it helped.